Okay, so we are proud and happy to have with us today Bernhard von Stengel from the Department of Mathematics of the London School of Economics. He has editing roles in MOR and IJGT. His interest in game theory ranges from the classic fundamental mathematics involved in equilibrium, as we will see today, to the very contemporary topics like multi-agent reinforcement learning and so on. Bernhard, stage is yours.
So thank you very much for the invitation. I think it's the second time that I have the honor to speak here. I think I was the second speaker in this series, and I'm again. So that's very nice of you. Now, contemporary is not exactly the topic that I'm talking about today. It's about a 70-year-old story that when you learn about linear programming and complementarity, you also learn that you can apply to zero-sum games, maybe. And definitely the other way around, you prove the Minimax theorem using linear programming. And typically these problems are considered equivalent in the sense that you can conclude one result from the other. And in fact, there's a story to that, you know what, I have, let me kill, I realize I have the wrong, 1 second. I use another, I'm coming back to you in a second. With another reader and share again, 1 second. Share screen, because that has a much better mouse. So, and then make this one, sorry about this. It's working okay? Can you see?
Yeah.
Okay, good. So, you know, von Neumann was it starts with von Neumann in a sense. We know him for the Minimax theorem. He was a universal genius. And in fact, I read a recent biography by him, which was actually, I can recommend highly. It's called The Man from the Future. And there's a story where Edward Teller, who worked with von Neumann on the atomic bomb, said, von Neumann would carry on a conversation with my 3-year-old son, and the two of them would talk as equals. And I sometimes wondered if he used the same principle when he talked to the rest of us. So I found that very funny because von Neumann was clearly above everybody. So in particular, Dantzig had worked on linear programming. And from a book by Dantzig, I have the following story where he walks into von Neumann's office, tries to explain it, and von Neumann gets impatient and he says, Dantzig, okay, if he wants a quickie, he can have it. And he says, in under 1 minute, I slapped the background on the blackboard, a geometric and algebraic version of the linear programming problem. And von Neumann stood up and said, oh, that. And then he gives him a 1.5-hour eye-popping lecture for Dantzig on linear programming duality. And von Neumann says, well, don't think I pull all this out of the head like a magician. I have recently completed a book with Oskar Morgenstern on the theory of games. I conjecture that the two problems are equivalent. So this is the topic of my talk here, the equivalence of linear programming and Minimax. And Dantzig said, well, thus I learned about Farkas's lemma and duality for the first time. Now, okay, so let's go into the mathematics. By the way, Phil Rainey and Ben Brooks have written a similar paper to what I've been doing and use the same story to introduce their problem. So I'm not sure whether Phil is here. Are you? I'm not sure. Okay, so mathematics here, just a bit of notation. I will use matrices, also transposed matrices, and always column vectors. The 0 is the all 0 vector, 1 is the all 1 vector. So A times X is a linear combination of the columns of A, and Y transposed, so that indicates a row vector times A, is a linear combination of the rows of A. And in particular, when you write Y transpose B, that's a scalar product of Y and B, so a row times a column. And I always treat scalars as 1 times 1 matrices, so that the matrix product works, because that simplifies a lot of thinking. So if you multiply a scalar with a vector, it should be behind it if it's a column vector, X times alpha for a scalar alpha. And if it's a row vector, it's alpha times Y transpose. Just in case you wonder why I put them there, that's where they belong. Okay, so now let's look at linear programming. The standard problem in inequality form says the following. I have a matrix A and the right-hand side B and non-negative vector variables X such that I maximize a linear function C transpose X subject to upper bounds, AX less than or equal to B. So these are linear functions bounded by the right-hand side from above. And there is a so-called dual program for this thing, which reads the same matrix vertically. We see it in a second. It uses the right-hand side and as an objective function, which you minimize subject to non-negative constraints for these variables y, and such that in each column you get at least the objective function vector as a result. So y transpose A is greater than C transpose. Now, why do we do that? Because if both of these programs happen to be feasible, meaning they have solutions, you can show that there are mutual bounds in the sense that everything on the right here, y transpose B, is an upper bound on everything on the left, which is actually the motivation if you look at it. And why does this hold? You just put the thing here in the middle, or I mean the y transpose AX, or write it like this. You have y transpose A minus C transpose, which is a non-negative vector by the dual constraints, times a non-negative vector X. So that's a non-negative number. And similarly for y times the slacks in the rows, which is exactly these inequalities. And so the effect is that any of them are mutual bounds. So if we can find two feasible solutions where they are equal, they're automatically optimal, because for any other solution, I mean, we have the inequality. So that's weak duality. And if we have the equality, we automatically know optimality. And the strong duality says that this is indeed always the case. If the two programs are feasible, then there are actually two solutions which have equal value, and that certifies optimality. And that's the strength of this theorem, that this always exists. And in particular, can also characterize it by the fact that you have to have equality here in these non-negativities, meaning these two vectors here, the vector of differences in the objective function and the other variables here. Let's look at the right-hand side, this may be easier. So B minus AX times this vector y, these are two non-negative vectors. They have to be zero in order to get optimality. And that means if one component is positive, you have to have equality on the other side. So that's called complementarity. I mean, they are orthogonal, these two vectors, and similarly here. And this is also called complementary slackness. We come back to that a bit later. And let's also recall the Taka diagram, which is a very useful way to visualize these linear programs. You write the matrix A in the middle, the right-hand side B on the right, less than or equal to, and have non-negative variables in the columns. Now, to these non-negative variables correspond dual constraints, where you read vertically y greater than or equal to 0, here corresponding to these inequalities. And then it's greater than or equal to the objective function value, which you maximize on the primal side, minimize on the dual side. Is there a question? I hear some noise. Maybe let me make my loudspeaker bigger. 1 second. Okay. So I hope that's familiar to you. And now let's look at zero-sum games, even more familiar to you, obviously. Here we look at finite games. We have a game matrix M times N. We have the maximizing row player who chooses a row simultaneously with the column player who chooses the column J in the row and column set respectively. And we have the payoff to the row player as the corresponding matrix entry, which is the cost to the column player. And we use now, this is the thing, I had to jump over my shadow, as you say in German. Normally the row player is player 1, the column player is player 2, and I try to use the alphabet in that order, but because we use linear programming terminology so much, I've chosen to use Y as the set of strategies for the row player and X for the column player, which violates, but that already is happening with M and N, then alphabetical order, but otherwise we get very confused with linear programming terminology. So to repeat, Y is the set of mixed strategies of the row player, X of the column player, and lowercase vector are the mixed strategies. So then you get the expected payoff and cost Y transposed AX when they play these two mixed strategies, Y and X. Now, a best response can be computed as follows. Suppose we have a column player, a minimizing strategy X. In each row, so that gives you the vector of expected payoffs A times X, and in each row I, you get the expected payoff in row I, which I write as AX subscript I. Now you have to expect that the row player maximizes this by choosing Y in correspondence, and we know that the maximum is already attained by the pure strategy. So the maximum of over YAX is in fact the maximum of the row payoffs, which in turn is the least upper bound of these finitely many numbers, V, I mean, greater than or equal to AX1 and so on. So you can write it as the smallest value V such that in each row you pay at most V, AX times the one vector times V. So that's what you have. And that's in fact the minimization problem of the column player. If you try to find a min-max strategy, you try to do exactly that. You try to minimize the V that you have to pay in each row. And similarly, a max-min strategy, a mixed strategy of the row player is one that maximizes the number U that you get in each column, which you write by looking at your own mixed strategy Y transposed A, which is a row vector that indicates what the other person has to pay in each column. You try to get as much at least in each column with this value U. So that's your max-min value, in fact, in max-min strategy. By the way, the good thing is here that these things exist, min-max strategies and max-min strategies, whereas in linear programming, they might not exist because they might have infeasibility. So that's something we have to come back to. Now, this minimization problem for the column player, say, can be written as a linear program, AX less than or equal to 1 times V, where X is in X. Now, X in X means the components of X sum to 1, and they are non-negative. I've written this here. And this is, in fact, a linear program. If you take V as a variable, you can move it to the left as a unconstrained variable on the left. You have -1s here. You do the same thing with the duals, here U down here. And in fact, then you get for free the constraints that these other variables Xj and Yi sum up to 1. And this is the maximization problem. I mean, in fact, minimizing V means maximizing minus V. And here, and the strong duality theorem of linear programming now gives you equality, meaning these two objective functions are equal. And hence you have min-max equals max-min, or the other way around. So that's the Minimax theorem. So that's what I have here. Every zero-sum game has a value, max-min over Y and X, YAX is equal to a value V, which is the min-max value on the other side. Trivially, only you have less than or equal here, which is like the big duality theorem. And also one little note, you might, if you write this inequality here by saying, well, for every, if you plug in the specific max-min strategy and min-max strategy X, so you put in this here, the Y hat, you have here the minimum of YAX is equal to YAX hat, X hat, sorry, and so on. So you can write it as a set of inequalities, which means here, when you look at this payoff, that actually you see that X hat is actually a best response to Y hat. So this equality on the left-hand side refers actually to the column player, and here to the row player. So it actually has a different meaning, and it's in fact the equilibrium property. And by the way, if you don't remember that, you can easily walk into your lecture and get very confused about showing that the existence of an equilibrium is equivalent to the Minimax theorem. It has happened to me. I had to give up after 5 minutes. I probably would have solved it. But remember that these inequalities are not what you expect them to be. And of course, I mean, Nash equilibrium can be proved via the fixed point theorem. We don't need that. We only need linear programming, as I just showed. And now the main question that I want to address is, so we see the Minimax theorem is a consequence of the strong linear programming theorem. The question is, what about the converse? And now I go into something which is considered folklore, and which has a big bug in it, which I'm going to fix. By the way, von Neumann said the two theorems are equivalent is not a good way of talking. any two theorems are equivalent, namely to true. And what he means, because I mean, a theorem has no free variables. What you mean is that they are easily proved from each other in the sense that you can instantiate the variables of one theorem from the other one. So I'd rather use the terminology saying one proves the other rather than implies, because implication is a logical thing, proving is a longer story. Okay, so now here is Dantzig's so-called proof of the LP duality theorem from the Minimax theorem. We have this set of these parameters A, B, and C, and we put them into a skew-symmetric matrix where I have here A and minus B, minus A transposed and C. These are the objective functions for the dual, sorry, for the primal, and the right-hand side for the dual. And then here, I mean, the transposed vector of this is a skew-symmetric matrix B. And that means as a game, it must have, if it has a value, the value can only be 0, because either positive or negative cannot work. It's a symmetric game. The value has to be 0 by the Minimax theorem. I mean, it exists. And so there is an optimal strategy for the column player, and which is identical to the one for the row player. And I call it YXT. So Y is how to play the rows, X how to play the columns, and T is single real variable, non-negative and a mixed strategy. So summing up to 1, such that BZ is less than or equal to 0, which means the column player can guarantee to not pay more than 0 in each row. And then automatically the same strategy also guarantees, because of this symmetry, that the row player with the same strategy will get at least 0 in each column. Okay, so this is a solution. And when you spell this out, BZ less than or equal to 0, you have from the first row AX minus BT is less than or equal to 0, minus A transpose Y plus CT is less than or equal to 0, and then BY minus CX is less than or equal to 0. Now, if you look at this on the right-hand side, it says the objective function of the dual by is less than or equal than the objective function for the primal Cx, which is exactly the opposite inequality from the one you automatically have from the big duality theorem. So if this thing on the right-hand side holds and these y's and x somehow solve the LPs, they're automatically optimal. That's the idea. And indeed, we get there if t is positive. And in fact, if the two things are feasible, there is such a t. Sorry. Then you have ax less than or equal b times t, divide by t, and you get both x and y as both feasible, and because of this right-hand side divided by t is preserved, optimality. So in other words, if t is positive, you have the dual and primal optimal solutions. If t is 0 and the bottom row happens to be negative, so by is less than cx, then the following happens. And we have to look at that, and it will turn out that this is the case when at least one of the programs is infeasible. We will shortly see why. Well, then I claim then either by is negative or cx is positive, strictly negative, positive respectively, because if that was not the case, you would have by greater than or equal to 0, greater than or equal to cx, and not by less than cx. So one of the two inequalities has to hold. And because t is 0 here from this equation, you have ax is less than or equal to 0, and y transpose a is greater than or equal to 0. So now I claim, let's look at one of the two cases. Say 0 is less than cx. I claim then this means the following. So either the primal is feasible, ax is less than or equal to b for some non-negative x bar, ax bar. If it's not feasible, we already know infeasibility. If it's feasible, we do the following. We add a multiple of, so alpha with a positive number, alpha times the alt x, where cx was positive, to x bar. And because ax was less than or equal to 0 in each row, this inequality is preserved. So this is always feasible for any alpha. And now c times x, this expression here is c times x bar plus cx times alpha, and this was a positive number. So this tends to infinity as alpha goes to infinity. In other words, the primal LP is unbounded. And for that reason, the dual cannot be feasible, because if it was feasible, it would establish an upper bound. Any dual solution is an upper bound to the primal. So we have here an infinite ray as a witness of infeasibility. And the same thing would hold if we had, say, by less than 0 and the dual was feasible. It could happen that both are infeasible. That's perfectly fine. But I mean, anyhow, if t is 0, and we have the strict inequality at the bottom, we have infeasibility. So we get the strong duality theorem that says either the primal and dual are both feasible and then have optimal solutions with equal objective functions, or at least one LP is infeasible and the other, if it's feasible, is unbounded with an unbounded ray. So that's a slightly stronger version of the duality theorem. But in fact, it follows already from the first part, the bottom part. Are there any questions so far on this story? Okay, so let me raise the problem. The problem is, and this is explicitly acknowledged by Dantzig and by Kuhn and Taka, who used this, we have not talked about the case that we have the right-hand side being, I mean, the last column played with probability 0, but we have equality in the bottom row and correspondingly in the right column. What this means is that we have a best response because it has a row value 0, which is unused. So we have an unused best response. And in this case, we have no information about the linear program. We don't know what happens. It could it be possible? We don't know. The proof is simply incomplete. And it looks like an innocent condition because this seems to be a degenerate case. Why do we worry about it? In fact, Lutz and Reifer in their book, or Lutz and Reifer in their book, Games and Decisions, claim that actually one of the two has to hold automatically. So let me write it a little bit more abstractly. If you have a skew-symmetric matrix B, say a K times K matrix, there is a vector Z non-negative such that the column player gets 0 payoff. At most has to pay 0, at most 0 in each row, and either place the top, this right column with positive probability, or in the bottom row, we have strict inequality. In fact, you cannot have both, it's one or the other, but they claim this holds. So they claim that you automatically have this as without proof. And in fact, it is true, but it's actually a massive theorem. It's called Taka's lemma from 1956. And let me show you why it is such a massive thing. This is the first thing I want to point out. This assumption here amounts to something massive. The assumption that we need for Dantzig's thing to go through. So to repeat, we have a skew-symmetric matrix such that there is we can assume, so Z will clearly not be 0, can be scaled to be a probability distribution such that it's a minimax strategy for the column player. And either the last column is played or we have a positive slack in the last column and row. Now, applied to my little innocent game from before by Dantzig, where C is equal to 0. So this is the special case where C is 0. It means that there is a vector Z given by y, x, and t non-negative such that first row ax minus bt less than or equal to 0, second row minus at y less than or equal to 0, b transposed y less than or equal to 0, because we now have no c here. And this is the special assumption here in the box, t minus b transpose y is bigger than 0. Okay, now let's look at this. If t is 0, we see that there is a y such that y transpose A is non-negative. And because t is 0, and this means minus b transpose y is positive, it means y times b is negative. There's one case, or if t is positive, it means there is an ax, there's an x, sorry, non-negative, such that a times x divided by t, so there is ax less than or equal to b. Now, if you read this, it is actually a version, the inequality version of the lemma of Farkas, meaning either ax is less than or equal to b for some non-negative vector x, Or there is a kind of separating hyperplane, y times a and y times b less than 0 with y non-negative. That's because you have an inequality here. So in fact, this assumption, Taka's lemma, implies the lemma of Farkas. And the lemma of Farkas implies linear programming duality directly. You don't even need the Minimax theorem or anything like that. So we can, it's not a proof, because we have already all the assumptions that we need to prove linear programming duality, and we don't need the Minimax theorem. So that's why this is such a massive mistake, in a sense, to make this assumption. In fact, let me go through a few variants of Taka's lemma. So here's a general story. We are talking actually about homogeneous inequalities, bx less than or equal to 0 here for a skew symmetric matrix. We can write it with this skew symmetric matrix, with this complementarity in the last column. We can also state it for a general matrix, A, and then it says the following: there is a non-negative vector x for the columns, y for the rows, such that so there is this row space vector which is non-negative, ax is less than or equal to 0, and now we have xn is non-negative, yan, this last column, is also non-negative, but at least one of them has to be positive. So that's what this states here for a general matrix. Or let's look at the bottom row. You can state it with equalities, where the only difference is that y doesn't have to be non-negative, but you have ax equals to 0 here, meaning x is a non-negative vector in the kernel of the row space, ax of A. And then you can find a linear combination of the rows, which is non-negative, such that you have a positive component either in x or in these inequalities for the row vector in the last component. And these are easily proved from each other, these two versions, these three versions. For instance, here, going from here to here, you will simply symmetrize. If you have A here, you take this skew symmetric matrix B, and when you look at Z, then Y and X does the job down here. Going the other way around, you simply plug in A. I mean, you look at A as the special case of the skew symmetric matrix B, and in order to symmetrize the Z here in Z non-negative and BZ less than or equal to 0, you simply take the sum of the Y and X that you have down there. And for the bottom row, it's also a standard story. You write the inequalities, these equations, as two sets of inequalities. Then you get two y's, which are non-negative, but the difference of them is an arbitrary vector y. And going the other way around, in order to write ax less than or equal to 0, you write it with equations by introducing slack variables s with an identity matrix. So the existence of slack variables that are non-negative, that fulfill s plus ax is equal to 0, is equivalent to saying there is some x non-negative such that ax is less than or equal to 0. And then these constraints here for the y introduce the non-negativity for the y up here. So these are totally standard constructions. They also are known for the Farkas lemma. Okay, so these are three versions of Taka's lemma. And now comes a story, another story, which I also find a little bit amazing. When you look at Taka's proof, and he stated that we have already shown that it implies Farkas lemma, the lemma of Farkas. In fact, the other version is also true, almost with the same lack of effort. I mean, or very little effort. And I'm surprised about that, because Taka thought, apparently, that he proved a much more general theorem. It's more convenient, but I don't think it's more general. It's another version, and I show you. So we use the following lemma of Farkas here. Either there is a non-negative vector x such that ax is equal to b, meaning b is in the non-negative convex hull, I mean, it's a non-negative combination of the columns of A, or if not, then there is a separating hyperplane, y times A is non-negative, y times B is less than 0. I write these theorems of the alternative, that exactly one of the two holes, always in such a way that the non-trivial direction is the one from left to right. Going from right to left is easy to see. So I apply the lemma of Farkas to the following. I put the matrix, the right-hand side B, as a negative thing into A. So I look at the matrix A, and now, or do it the other way around, let's put the AN on the right-hand side. So according to the lemma of Farkas, either minus an is a non-negative linear combination of the first n-1 columns of A. And then I do the following. I look at the vector x, which is z and 1, and simply set y to 0. Let's see what I'm after. I want to prove the lemma of Taka. Well, in that case, x is non-negative because z is non-negative and it has a component 1 in the last component. That's what x has. Now y is 0, so we have trivialized that y times a is non-negative. I have ax is equal to 0 because of this equation here. That's how it was designed. And I have the sum here is positive because xn is equal to 1. Okay. Or Farkas says, well, if that is not the case, if the negative left column of A is not the non-negative linear combination of the others, well, then there's some vector y such that y times aj is non-negative for the first n-1 values of j. Y transpose n times minus an is strictly negative. So in other words, y times an is strictly positive. And I just set x to 0. And then I have the same set here. We have trivially x equal to 0, this by construction. And now we have xn is 0, but yn is positive. So that's exactly the lemma of Taka in one of the versions that I just shown as a very easy consequence of the lemma of Farkas. So in other words, I think they are almost, I mean, they are more or less identical theorems. Okay, which surprises me because Taka didn't point that out. So to summarize the whole story so far, Dantzig constructs a specific game, but his assumption for then deriving from this game the strict duality theorem, the strong duality theorem, assumes Taka's lemma, which amounts to the lemma of Farkas, which proves linear programming duality directly. So we don't actually use the Minimax theorem here, because we can apply the lemma of Farkas directly to proving LP duality. I have not shown you how. It's actually in my paper about this talk, but okay. So, and now the story next is the next 10 minutes. I will fix this by following a paper which did address this whole in Dantzig's proof 9 years ago in the International Journal of Game Theory by Adler. Is Ilan here? I don't think so, but so this was actually the inspiration of this to some extent. Oh, Ilan is here. Hi, Ilan. Good to see you. Well, I don't see you.
Yeah,
but,
hi, thanks.
Yeah, very good. So Ilan is actually the main motor behind the whole story. You might see my paper, and I hope I probably might not have acknowledged you enough there, but I've distilled from your thing the following proof, which I think is a somewhat shorter version of what we are doing, but it's exactly following the blueprint of the last section of Adler's paper, of Ilan's paper. So in order to do that, I go one more time to Taka and I show one, what is called Taka's theorem rather than Taka's lemma. Now recall what it says, sorry. X, there is an A, x greater than or equal to 0, y, these two vectors exist, namely ax is equal to 0, non-negative x, y times a is greater than or equal to 0, and we have strict complementarity. Now, originally it states this, actually the Taka states this for the first column, I stated it for the last column. In fact, it can be stated for any column. For every column, there is such a j. Now, these are homogeneous constraints. In fact, that's the title of Taka's paper, Homogeneous Inequalities. So we can sum them all up, they will all be preserved. And when we do that, we get actually vector x and y. I mean, obviously these were x and j's, y's depend on j, but the sum is the sum here that has the following property that x is non-negative. The row vector that I combine with y is also non-negative. Ax is 0, so x is in the kernel. And we have complementarity in every column. So either xj is positive or the corresponding column of ya is positive. It is very easy to see that you cannot have both because that would contradict that ax is equal to 0 because that would not vanish ever. It would become a positive number. So you can have only one. We have complementarity in every column. And obviously then also in the last column. So it is, this is called Taka's theorem. And it obviously implies the lemma because it holds for every column, in particular the last or the first. And it's a very nice way of stating it. With a skew-symmetric matrix, there is a vector z such that bz is non-positive, z is itself non-negative, and z minus bz is bigger than 0. I mean, you could write it with a plus, but this is the way of looking at the game, where you have for every z in each row, I mean, what you want from the column player. And it means actually it's a quasi-strict equilibrium, because z is obviously non-zero, and it can be normalized then to be this homogeneous, to have length one norm, so it's a probability vector, and it means every best response has positive probability. That's what this theorem says. Okay, so I go now to two theorems that are much older than that by two German mathematicians, 42 years apart in the same journal. Stiemke, 1915. By the way, these papers don't talk about matrices, they manipulate equations, but in modern language, that's what they state. So Stiemke's theorem says the following, and this was actually used by Gale, Kuhn, and Taka to prove the Minimax theorem for symmetric games in the famous paper on symmetric games. They use Stiemke's theorem. It says the following: if there is no non-trivial, non-negative vector in the row space of A. So in other words, whenever you have y transposed A is non-negative, then the only case where this happens is when this is the zero vector, obviously with taking y to. So if there is no non-trivial, non-negative vector in the row space, then there is a strictly positive vector in the kernel of A. Okay? And again, only the implication from left to right is non-trivial. Okay, so that's Stiemke's theorem. Gordan's theorem says almost the same, but phrased differently. It's not the same. It says if the only non-negative vector in the kernel of A is the zero vector, Gordan says there is no solution, but I mean, it's of course there is a solution, a trivial one. Then there's actually a strictly positive linear combination of the rows. And Stiemke, in fact, proves Gordan's theorem by talking about orthogonal complements in modern language. He doesn't cite Gordan. It's the same journal. Sure enough, I mean, he hasn't read that part. We only discovered it later. And I'm pretty sure it happens because 42 years later, I mean, the editor was long dead that handled that paper by Gordan. Nobody remembered it. So Stiemke proves Gordan, and again, I've actually reproduced Stiemke's proof because it's in German in my paper. It's a nice and compact proof, and it has actually strong similarities structurally to Taka's proof of his lemma. So have a look. I mean, I hope you enjoy that. Now let me show you the strength of Taka's theorem here. Taka's theorem here says x is non-negative. Y the row, so we have x non-negative in the kernel, the row vector, the row space vector, which is non-negative, and you have the complementarity here. Now let's look at Stiemke's theorem as a special case. Why? Because it says if the only row vector, the row space vector, which is non-negative, is 0, then there must be such an x. Well, we get it here from the complementarity condition from Taka, because ya is 0, so x is actually strictly positive. So that's one special case. Gordan's theorem is another special case. If the only non-negative vector in the kernel is the 0 vector x, well, you have this y here, so x is 0 here, and then you have y, the vector y transpose A in the row space, which is strictly positive. So you see that up here. So you see that Taka implies both Gordan and Stiemke very easily and immediately. There's another theorem, which is due to Wille from 1938. I don't think Wille quotes Gordan either. It's the inequality version of Gordan's theorem, which says either there is a so let's look at it. If there is no non-negative vector x such that other than 0, such that ax is less than or equal to 0, then there is a linear combination of the rows, such means this element in the row space is strictly positive. Now I claim this is almost a Minimax theorem. Let's think about it. The left-hand side says the column player, the minimizer, with a payoff matrix A cannot guarantee a 0 payoff for each row. Okay, the column player cannot guarantee value 0 for each row. That's what the left-hand side says, because x non-zero means you can scale x to be a probability distribution. That's what the column player cannot guarantee. The minimax value is positive. And then it says the row player has a way of exploiting that by getting every row to be positive, every column to be positive. So that means the role player can guarantee a positive payoff for each column. And in fact, Wille used this to prove the Minimax theorem. I mean, it's very easy. You just subtract, I mean, the Minimax value from this, and then you get a Minimax from Wille. So Minimax implies Wille implies Gordan. That's what we have to remember. Okay, so here is the story. And as I say, inspired by Ilan Adler's proof, but in a slightly more direct way. So let's look at the non-negative vectors x in the kernel of A, ax equals to 0. And I look at the vector or the support of the vector that is maximum. Why does this exist? Well, any two such vectors, the sum of them fulfill the same equation. It's a homogeneous equation, and non-negativity is preserved. So if the support, which is the set of columns which have positive probability under these vectors, of the sum is clearly, I mean, the support of the sum is clearly the union of the supports. So there is clearly a maximum support among all the vectors that fulfill this. I call this set S. And I call the other vectors, the other columns J, so they never appear in a kernel with a positive probability if all the other components are non-negative. And I write AX by splitting it into the columns indexed by J and the columns indexed by S as AJXJ plus ASXS. And that's my the vector of column coefficients X. So the main idea is that we can actually eliminate, this is Ilan's idea or Ilan's trick, that we will be able to eliminate these variables XS from the system, which then allows us to use Gordan's theorem, which talks about the only zero variables. So that's the main story. Let's see how we do that. So I have split here the vector, the matrix A into AJ and AS. This is XS, which has a positive solution with XJ is equal to 0. And what I want in order to prove Gordan's theorem is a vector Y such that if you linearly combine the rows of A, you get equality here. You actually need equality here. There is no way around that. But strict positive numbers here on the left. That's what you want. That's what Taka's theorem states. And here's how we proceed. We assume AS has a certain rank. It could be the full rank. It could be 0. Let's look at a general thing. In fact, I look at the bottom row here, which is actually so let's look at the set of spanning vectors, independent rows of, in fact, I should call it the basis of the row space of the matrix AS. So these are spanning rows, in fact, linearly independent. That's what I want. I didn't say that, but that's what I mean. So every other row up here in a matrix AS is a linear combination of these bottom rows F in the matrix F. So in other words, what I'm doing now, I'm rewriting the system AX equals to 0 by doing some row operations that subtract all these multiples of the bottom rows from the top, from each top row, such that this part here becomes 0. In effect, what I've done here is I've eliminated this way the variables XS from the top system. That's what I've done here. It's a totally equivalent system. You can write it with a matrix C, which is upper triangular. And it says simply AX equal to 0. You multiply by CX. And no matter what rank A has, I mean, the C will be full rank, will be just an upper triangular matrix written in this way. And it has the form that C times AS has the shape that 0 and F here. So that's what the new system is. E times XJ is equal to 0. E times XJ plus FX is equal to 0. So that's just an equivalent system to AX equal to 0. And this is amounting to eliminating the variables XS from the top set of equations. And now I will use Gordan's theorem to find the vector W such that W times D is positive. And I have to prove that the assumptions of Gordan's theorem holds. And then W times 0 with the matrix C plugged in will actually be my Y for Taka's theorem. We will see it. So just to repeat, we have here X tilde, which is non-negative, has maximum support, which is positive here. And I can rewrite AX in this form that I just described. DXJ is equal to 0. EXJ plus FXS is equal to 0. So now question, can we have anything in the row space of D? Sorry, can we have anything in the kernel of D which is non-negative and non-zero? I claim not, because I'm now using the fact that F is, has full rank here down here. So if there was, I could solve this system as follows. I look at the matrix E, which I have here times xj. So this is the purported xj that I think exists, and solve for some xs. That's not unique because F is typically has more columns than rows, but anyhow, there is such a vector fs because F has full rank, and it will fulfill this equation. Now, the only problem is that xs is not necessarily non-negative. But here we use the fact that there is this x tilde x, which is strictly positive. And we use the homogeneity here, x tilde here. We can add any multiple of x tilde to my vector here. Remember that x tilde has 0 components in xj. And these are the only positive ones. So if we make alpha times xs large enough, we actually do get a positive vector here, which solves the equation. And xj was meant to be non-zero. So that would mean, however, that S was not of maximal support. That's a contradiction. So in fact, such an xj doesn't exist. Okay. So the maximality of S we have exploited here, and we have used this elimination of variables by putting them back in with a positive vector and put that here. And so now we can use Gordan's theorem, which says now there is a strictly positive vector in the row space of D. Yeah, there's some vector W such that W times D is strictly positive. Well, if you plug that in the original system, we have W and 0 times C. So that will add extra components here in the bottom row. They're not necessarily 0 anymore. But times AJ is strictly positive. And times AS, the whole thing is, so Y times AS is equal to 0 by construction. If you look at this here, you see W times 0 is 0, and 0 times F is also 0. So we have our vector Y, and that's Taka's theorem. So the trick was to maximize the support. If you understand Taka's theorem, you see that's the natural thing to do. You maximize the support. And then for the rest, you can apply Gordan and thereby have the solution. And I think that's, I think you should have been able to follow this proof. Okay, with not too much computation. So let's summarize. Dantzig games, we actually do use Dantzig's games now in an actually very nice way to prove not only LP duality, but something stronger. Remember, Dantzig's proof assumed Taka's lemma, but what we do now is doing something different. We use the Minimax theorem to first prove Gordan's theorem. This is, fairly straightforward technical. The non-trivial part I've just shown you. We prove Taka's theorem, which applied to the skew-symmetric matrix Z means BZ is non-negative, Z is non-negative, and we have strict complementarity in every column and row. And now we not only get linear programming duality, but assuming that, we get the previous story, if they are feasible, we have optimality, but we have not only optimality, but because of the strict complementarity, we actually also have strict complementarity in the LP solutions, actually with a unique support, which is a very useful theorem in certain contexts. In other words, there are LP solutions such that every inequality is either strict or the corresponding variable is 0. But you never have a non-strict inequality where the corresponding variable is also 0. So you get an actually even nicer version of LP duality. And we have, in some sense, salvaged the Dantzig game, which I think is another nice aspect of this story. So that is my proposed repair of proving LP duality from the Minimax theorem. By the way, even this proof here at the top, even Schreiber, who is sort of Mr. Linear Programming, has echoed Dantzig's proof, but overlooked the strong assumption that was underlying here. So that's the main story. And I have a few other things that I would like to tell you, but I'm happy also to start a discussion now if you want. if you want, or I can say some more goodies that I think you might be enjoying. What would you like me to do?
Well, you have the time to tell us more.
Tell us more. Okay, good. And you can also, of course, ask later. So what I want to tell you, and I got this from Sylvain and Rita and Jerome's book, is the proof by, and it made it into my book. You should by now know of my book. This is the proof of the Minimax theorem, which everybody should know. And it's due to Loomis from 1946. And I'll tell you a little bit later why it was not recognized so much. So here's the story. It's really a wonderful proof of the Minimax theorem. So we know that the min-max strategy exists, which minimizes V such that AX is less than or equal to V in each row, meaning the column player, the minimizer, pays not more than V in each row. The max-min strategy guarantees you U in each column. You play Y, and the linear combination of the rows gives you at least U in each column. And it's easy to see, I mean, trivial, in fact, that U is at most V. So by simply plugging in Y, AX in the middle. And now a first observation is, if you had equality throughout, if every row would be giving you V and every column would be giving you U, if you had equality, then you would already have U is equal to V. In particular, say if you have a 1 times 1 matrix, this is an induction proof, by the way. If you have a 1 times 1 matrix where you have no choice, you have clearly U is equal to V. So if the dimensions of the game are very small, namely 1 in each M and M, then you have the theorem already. So the interesting case is that there is some row or column which has less than what you can guarantee, or more than for the column. Let's assume for the row player, there is some row that when you play your minimax strategy X, some row K, you actually pay less than V. The same thing happens when you have such a thing for the column. We just do it for the row here. It's just a completely analogous course. So let's look. There is some row K here, and now I delete this row from the game, which is a game which has smaller dimensions, and by inductive hypothesis, it has a value V bar with a minimax strategy X bar, such that A bar X bar is less than or equal to 2 times V bar. So there's a new minimax strategy for the game where the row player has 1 row less, and where now you have V bar, which is what the column player can guarantee to pay at most, and what the row player can get at least with V bar. So we have V bar is less than or equal to U. No, why is that? Why is that? Because this game, this is easy to see algebraically, but it's also intuitive, because this is a game where the minimizer is cannot use 1 row, so he cannot be better off. So V bar is at most equal to V. And the U bar that we would have is less than or equal to U, but we know already that's equal to V bar. Okay? So the problem is, I mean, that if V was bigger than V bar, we would know nothing. But the claim is that actually V bar and V are equal. And the intuition is that the maximizer, the row player, doesn't use that row of A anyhow. Okay? So we prove now that V bar is equal to V. This was how we, constructed the whole thing. Remember that AX in row K is actually less than V. And we have these inequalities. So suppose V bar was less than V. Now I look at the following construction. I sprinkle in a little bit of epsilon with the positive epsilon of my minimax strategy for the smaller game X bar. If I do that, and I know that I get less than V bar in the smaller game A bar, sorry, we know then by linearity, this is actually V minus epsilon times V minus V bar. So this is less than, you can actually fairly obviously pay less in each row other than K less than V. Okay, so we reduce the payoff in all the rows except K by some small amount. And now let's look at the row that was missing. We don't know nothing about what AX bar does. That could be a totally different strategy. That could be very bad for the column player. But we use it only with epsilon, and it was strictly less here in the original game anyhow. So if you make epsilon small enough and positive, it will also be less than v, because it was less so in the original game. Okay, we don't know nothing about here ax bar, but because we use it only with epsilon, we have less than v. But now we have found a strategy ax of epsilon, so x of epsilon, that gives you strictly less v than v in each row for the entire game, which contradicts the minimality of v. Okay, we have chosen this as the minimax value for the entire game. So v bar and v are equal. And now I just plug in v bar is less than or equal to u, less than or equal to u, which is equal to v bar. Greater than wouldn't help, but it's equal to. So we have u is equal to v, and deduction is complete. 5 minutes. Isn't that a beautiful proof of the Minimax theorem? I think it's wonderful, and it doesn't use any algebra compared to what we later on do with when we prove the LP duality. There is a little bit of linear algebra that goes into this. This is a completely analytic proof. Let me tell you, in my opinion, why this proof hasn't caught on. I think Loomis made the mistake by calling it on a theorem of von Neumann. He proved actually a more general theorem where he had an extra matrix B, which was strictly positive. If he had called it a new proof of the Minimax theorem, everybody would have noticed. On a theorem of von Neumann had so many proofs. Von Neumann themselves, they noticed it. In the second edition, they mention it. The same proof 22 years later, was proved by Owen. He hadn't noticed as an elementary, with a title on an elementary proof of the Minimax theorem. It is, in fact, the Minimax theorem when you plug in the all-one matrix. And in fact, it's not even more general, as Sylvain and so on show. I mean, by some continuity, if you have the Minimax theorem, you also get this more general theorem of von Neumann. Nothing gained by calling it on a theorem of von Neumann. So that's Loomis. And here's another gem which you probably don't know, which is the one for the Lemma of Farkas, where I tell you the whole story in this theorem. So this is it's a kind of an induction proof, but with a trick. Suppose you have a system of linear inequalities, ax less than or equal to b. It's infeasible. And I now throw inequalities away until it becomes feasible. I take one inequality back in. So it's minimally infeasible. In other words, it is infeasible, but as soon as you throw one inequality away, it becomes feasible. The claim, if that is the case, then the corresponding set of equations is already minimally infeasible. This is a theorem also proved not as simple. Anyhow, I put it in my paper too, by my colleague Zambelli and Conforti and Di Zuma. And just to give an intuition, when we have this theorem, if you reverse any inequality, well, let's take the inequality out. The original system becomes feasible. So this inequality has to hold in reverse, but it says then that the other ones hold with equality. So if you have that, this is an obvious, consequence of this theorem. And then I can use linear algebra. And that's again a point where linear algebra comes in when you want to prove Farkas, which says that if there is no unconstrained solution to ax equals to b, then there must be a y such that the linear combination of the rows is the all zero vectors, but the linear combination of the right-hand side is non-zero. So that's a theorem that says if b is not in the column space of A, you can do exactly that. So in other words, you can derive the equality A0 is equal to -1 from the system ax equals to b. That can only be if it's infeasible. It cannot be feasible if you could derive that from it. And now the story about this theorem is that you know that if you look at this thing here, ax less than or equal to b, because of this reverse story is y has the right sign. Otherwise, you would get a feasible solution. And in fact, that proves you that then there is this, you can derive the inequality 0 less than or equal to -1 from the infeasibility of ax less than or equal to b. And that is another version of the Lemma of Farkas. So with this slide, you could prove, this is an induction proof. Once you know the theorem, you could do all this on your own easily enough. Nothing difficult here. And it's a beautiful, less than 1 page of the Lemma of Farkas on its own, which is why both I and Giacomo Zambelli are slightly suspicious when people prove new versions of the Lemma of Farkas with some elementary proof that is 5 pages long. when you can do it all together in half a page. I think this is a good time to stop. I have more, but I show you what the chicken is if you care, but thank you.
Thank you. People, if you have questions, now is a good time to unmute yourself and ask them.
Sorry, I want to do something else here. I don't know how to get out of this. Yeah, okay.
So I send you an email with the address and the reference for this Lagavulin.
Okay, yes. Sorry, email? So I'm not getting quite. Should I stop sharing? I can stop.
Fine. If you want people to see. Okay.
No, tell me what's your question, Sylvain?
No question.
Okay. So by the way, the paper is on archive and it's also on my webpage.
Very good.
So now I have to ask about the chicken.
Okay. Maybe, I mean, this is, so what I wanted to say is I tried to explain, so when I wrote my book, I realized that I wanted to prove something else. I wanted to prove, well, anyhow, it turned out the following. I realized that the standard proof of the lemma of Farkas is actually, can be told in 2 dimensions about a triangle. And in fact, about the separating hyperplane theorem, let me put it this way. So you have a triangle and 3 points, corners A, B, C, and you have a chicken at point B, a bird at point B, who wants to do what? It wants to cross the triangle. Why does the chicken want to cross the triangle? This is a joke. You might know it, you might not know it. Why does the chicken want to cross the triangle? Come on. To get to the other side, of course. So that's so here's the story. And it's a mathematical chicken. It wants to get there as fast as possible. Now the story is that it crosses the triangle only if the angle here is acute. Okay. In other words, if the angle here is obtuse or right, I mean, meaning at least 90 degrees, then it will not cross the triangle, but walk along the side. Okay. So the closest point to get there is C, if and only if the angle at C is not acute. So if suppose C is 0, the origin, that means that the scalar product of A and B is non-positive. Okay. So otherwise you cross the triangle, you get a closer point, but other C is the closest point on the other side, if and only if the angle is not acute. And I claim that is the basis of the supporting hyperplane theorem, which says the following: if you have a closed convex non-empty set in Rm, B not in C, and you take the smallest point, the shortest distance in C to B, here the closest point here, and put the normal vector through this point on a hyperplane here to this point C, then C is entirely on this side of the hyperplane. That's what it says. Well, first of all, I mean, this is obviously a positive distance because C is closed, so it exists, the closest point C exists as positive distance. And here we have the chicken because the line AC in this triangle is in C because C is convex. So if the angle here was not obtuse, meaning it was bigger than 0, then the C would not be the closest point, it would come here. Okay, so it's a 2-dimensional picture that tells you the supporting hyperplane theorem, which is the basis of the lemma of Farkas. If you look at the closed convex cone, some little algebra extra needed to move the supporting point to the origin, but that's what I wanted to tell. I mean, you can tell the supporting hyperplane theorem at the dinner table by talking about a chicken in a triangle. That's what I wanted to tell you. Okay, so by the way, if you use this, you need also the closure of the cone, which is not trivial. you need theoretically, meaning use some basis vector and so on. So the linear algebra comes back in here through the closeness of the cone. Otherwise, you make a mistake too. So it's not that's the standard proof. I think that's the one that von Neumann and Morgenstern used in their original book. But there is some work here to do, and all the other proofs, well, not Gordan maybe, I mean, but the other proofs are actually, there are many other good proofs of the lemma of Farkas. Okay, so here's the chicken.
Thank you. More questions? Okay, then I stop the recording.